So, by the turn of the 1950s, we figured out that the Milky Way is a spiral galaxy. We have 50 plus years of advancement in our knowledge there, but we're just going to go into what structures do we understand now and step away from that history lesson. So, here's what we know. The Milky Way is composed of this central bulge of older stars. And in it, it's going to have several spiral arms. Milky Way has two primary ones and a couple of others coming off of that. Right? So in the spiral arms, you're going to have a lot of gas, a lot of dust, and, importantly, a lot of new stars. And then outside of that, there'll be this halo. Halo is going to be out here. You'll have another diagram in the next slide to see it. So we call this a top-down perspective. Here we're looking at an on-edge perspective of the Milky Way. We live about here, 2/3 of the radius of the Milky Way, away from that bulge, away from the center. And this is what I mean by that layer of dust. And here are globular clusters. Remember the clusters that Shapley used? Clusters like these is how he was able to get the size of the Milky Way. So, another perspective, once again, bulge, there's us. This would be the spiral disk. This area in this disk is where the spiral arms are going to be. And then you have this halo, right? And the halo is about a spherical shape. And in there is where you're going to find all of the clusters of stars together. In the Milky Way, there's an estimate of about 150 of these. And as you'll notice down this table, where mass is concentrated, the mass of the Milky Way is mostly in this disk. Right? If I'm looking at the thin disk here, the thin layers here, that's going to have the biggest amount. There's about 400, let's see here, trillion is 10 to the 9th. There's about 40 trillion solar masses in just the thin disk of the Milky Way. So if all of that mass was just individual Sol-sized stars, there'd be about 40 trillion of them. When you go into the thicker disk, just slightly above the thin disks, there's still a large percent of star mass there. Luminosity, about in the same scale. It's about 30 trillion million times the luminosity of the sun. And that just comes through the sheer number of stars inside the Milky Way. And so now we can say, well, where are the elements at? You'll notice in the thin disk, there's a lot of heavy elements. This will tie into basically what generation of stars are you at. Where did those heavy elements come from? Well, they came from the last generation stars dying and expelling the heavy elements that they fused in their cores at some point. So younger stars are going to have a greater number of heavy elements in them. Now, I don't want this to be confused with previous sections where we said, wait a minute, the younger a star is, the lighter the elements are. Right? We're distinguishing between what's going on in our previous sections deep in the cores of the stars versus this discussion here, the outer layers, the atmospheres of the stars. What's the concentration of heavy elements there? All right. So, going in the disk, you're going to have lots of heavy elements, right? And this gives credence to the idea that these are second generation stars, third generation stars. Whereas you go into that halo and you start going for older stars. There are going to be fewer elements in them because they are probably some of the first stars that ever formed. Being a spiral galaxy, the Milky Way has to have a couple of arms, and we'll break them down to two main arms. There's the Scutum Centaurus and the Perseus arm. And you can see the Perseus arm in this picture here. Right? That's what I mean by it being the main. It's one of the larger arms out there. And for the purposes of this course, we'll break it down into two additional smaller arms. There's the Orion Cygnus Spur. And along that Orion Spur is where you'll find the sun, where we live. And then you'll have the Sagittarius arm, which is this arm here. So you'll notice with the arms, you'll have these patterns of band of higher density stars, then a gap, then another band of stars, and then gaps. And that's the foundational density of the arms of a spiral galaxy. But if we look at some simulations, we're going to notice some weird conceptual things we need to figure out about what maintains these arms. So let's look at the spiral patterns. Where do the spiral arms come from? Well, you start off with basically two gas clouds that are a combination of stars and dust, and as they fall in towards each other, they'll naturally start to rotate. And that rotating pattern will eventually leave pockets of higher density that trace out the arms and lower density, the blank space. But there's an issue with this. You're going to have the fastest rate of rotation towards the center as things are moving the fastest due to just gravitational forces pulling them inwards. And as this thing spirals around, you would expect to do something like this, or as they rotate long enough, they get wound up. And you get what you're seeing right here now, this winding. Went back to the beginning, you get the spiral arms, and we would predict over a long period of time that you would just get these kind of circular blobs or elliptical blogs of stardust. And yet, we clearly see the spiral galaxies have been maintained for millions and billions of years. So one way to try and explain that is we've come up with this idea that's called this density wave propagation, where basically this higher pocket of density here allows for a wave to travel through. It's similar to sending a sound wave through the cup on a string, all right? You could whisper something in the cup, and because of the higher density of the string, it's able to transmit your signal across to the other side. Well, the higher density of stars creates this way for this wave to propagate across the entire galaxy and maintain the structure of the arms. Stepping away from the arms, we can talk about what kind of stars that we see. And we've categorized them into two main populations. There are more categories, but we'll focus on population 1 and population 2 type stars. Let's focus on the ones, right? You're going to have the galactic plane, where the central bulge is around here, and you'll have the spiral arms rotating around in this thin disk. That's where we're going to find predominantly these population 1 type stars. And there are going to be some bright supergiants and a lot of main sequence stars, especially O's and B's. So they are concentrated in the spiral arms because this is a region of star formation. There's a lot of dust, there's a lot of gas, and that fuels a lot of stars together. So these tend to be young in these open clusters. Remember I said, there's a lot of interstellar matter and molecular clouds floating around there because a lot of stars are being formed inside this disk. So there's a lot of activity in this region. And that's why we tend to find the population 1 type stars. Now switch to the other category. We go to our population 2s. And these guys are going to be found throughout the galaxy. Remember the galactic halo? Right? The galactic halo is that sphere that encompasses the entire galaxy. Well, you're going to find stars that have all sorts of strained orbits here. Whereas the population 1s, they tend to have these elliptical orbits around the central bulge. Population 2, they can have all sorts. They can have orbits that intersect the galactic plane, some that just go around. And these are going to be a lot of stars that are older, and many are surrounded by planetary nebula. Remember what a planetary nebula is. That is the oldest stars as they, as I like to say, burp up their outer layers. They're ejecting, creating new concentrations of gas that will fuel new star generations. So there's going to be a lot of variable stars inside these globular clusters. And these stars, like I say old, they're pushing 11 to 13 billion years old. And you might recall, I've made references before, the universe itself is only slightly older than 13 billion years old. So the stars that you can find in these population 2, some of them might be the very first generations of stars that ever existed. So, time to test our knowledge a little bit here. Which category of stellar population does Sol, our star, fall into? Is it a 1 or is it 2? Or is it an additional category? It doesn't quite fit in any of those. So, go ahead and pause the video, come right back. Welcome back. We'll identify that Sol is a population 1 type star. It's in the galactic plane. It's where we're going to find a concentration of stars. And like I've said before, Sol is a main sequence average star inside the spiral arms, inside the thin disk of the Milky Way. So continuing on, what other properties can we start to pull out of the Milky Way? One thing is, when we've got the spiral arms, let's look at their rotation rates as you go outside. So we're looking at a plot here is the rotation rate of the stars near the central bulge. 0 would be the exact center of the Milky Way. And we're sweeping out across the Milky Way, going further and further out. So we're in about this region. Right? And this is the predicted velocity, how fast. The bulge is going to have a lot of chaotic motions in the center, but once you get outside the bulge, you're going to expect this pattern of slowing down, speeding up, and eventually decaying. Right? And that's just as you're getting further and further out in the spiral arms. We expect that the rate that they're moving around to slow down. And that's because, well, the arms aren't solid, rigid objects. They're composed of stars and dust spread out over hundreds of light years. So we expect that as you get further away from the core, their speeds, powered by gravity, is just going to diminish. But then we actually look at the data. We sweep across the Milky Way. And yes, in the centers, we start getting the patterns we expect. But when you look out across the Milky Way, go further and further out, the arms are actually rotating faster than what we'd predict, much faster. And the only explanation we could think of for this is that the galaxy has a lot more mass. I don't mean like 10% more. We're talking hundreds of percent. Way more mass is in the galaxy. And we just don't see it. By looking at the rate these arms are rotating, we're starting to see indications that there is matter out there that we have not found yet. The next awesome thing that we've learned about the Milky Way is that the Milky Way has been in a lot of bruising and cruising through the cosmos. These bands we're seeing here, these are what we call tidal streams. It turns out the Milky Way has collided with other galaxies and basically absorbed all of their material into itself. So, let's go through these points, right? If galaxies come too close to each other, think of tidal forces, the moon on Earth. If two gravitational bodies get close to each other, there's this tidal stretching. And doesn't matter the scale of the universe, that still exists. Even on galactic scales, you can have gravitational tidal forces. And so if two galaxies get too close to each other, they'll eventually become gravitationally attracted and start merging together. We have two types of categories of this, but they do effectively mean the same thing. You could have a galactic merger, and that's when you have two galaxies that are roughly the same mass become gravitationally attracted to each other, and they'll start moving closer and closer until they finally collide and merge into one. Right? Then, basically, another version of that is what we call galactic cannibalism. Basically, you got yourself your big, massive galaxy and your tiny galaxy. And as they get closer and closer, the tidal forces start to rip apart the smaller galaxy. And the bigger one, we say, cannibalizes the smaller one and just starts pulling it into itself. So for the Milky Way, we've identified at least 12 of these streams of matter being pulled from other smaller galaxies. In fact, our galactic disk, the very material we live in, is probably a result of multiple collisions with other galaxies. So in local parts of the universe, galaxies are constantly moving towards each other, merging, cannibalizing, and being stuck together. So the Milky Way so far has been successful in colliding and gobbling up a couple of galaxies, but that's not the ultimate fate of our galaxy. Ultimately, we're going to get gobbled up ourselves. See, it turns out the Andromeda Galaxy is on a crash course with us. In about 3 or 4 billion years, we're going to hit. So let me put on this little animation. This is a simulation of the event. So that's going to be the Andromeda Galaxy coming towards us. And there's us in our galaxy, the Milky Way. And over time, their gravitational attraction will cause them to come together and eventually smash. You'll see stars and dust being flung out across the cosmos. And they'll keep repeating this process until they finally settle in. Their cores have merged together, and you'll have a new, larger galaxy. This one in this simulation is probably going to be a type of elliptical galaxy once it's all said and done. So, overall, in about 6 billion years, the Milky Way and Andromeda will have fused into one, cannibalized into one galaxy that, for now, we're affectionately calling it the Milkdromeda Galaxy. Now, remember back in that animation, how when the cores of the galaxies collided, you saw dust flinging out in the cosmos? They didn't come back. So, by our best estimates right now, solar system, our planet, it has about a 50% chance of being in the outer arms of the new Milkdromeda Galaxy. It also has a 12% chance of being that ejected material, the stuff that just gets flung out of the cosmos and is no longer part of a galaxy itself.